Hey everyone and welcome back to PrepFusion. I'm Anish and today we'll start the second lecture of choppers, basically DC to DC converters. So previous lecture was basically introduction and we learned about step down choppers with pure resistive load. Okay, we didn't had any inductor or all those things. Now in this lecture we'll include inductors and RLE loads. So we'll analyze for both these cases and then see what changes it makes. Because previously what was happening was our current was not continuous and it was discontinuous and we may not want that. One more thing is that previously I didn't had any like freewheeling diode type structure, right, in a step down chopper, and generally we don't use simple just R and simple this one switch in step down chopper. Obviously there are other elements as well. So other two elements, in case of other two elements, this is the diode that is present and an inductor will also be present, okay, in any of the choppers. Let it be step down, step up, or step up down chopper. In any case inductor and diode will always be present for providing in the path when the inductor has totally this switch has been turned off. Okay, so that's why that was for the understanding purpose, that was for the learning purpose. But obviously in practical life we don't use those type of choppers just with pure resistive and just with the switch. That is the simplest thing, right? So in RL load, what happens? We connect a diode anti-parallel. So basically what happens? It is a freewheeling diode. This diode provides a path when the switch is off. Okay, provides a inductor can get a discharge path when the switch is off. That's why diode is essential for design of choppers. And like while we will analyze, right, what assumptions we'll take, just same as rectifiers. That's why I'm going very smooth and very fast here, because all the basics have been cleared in rectified itself, right? Analysis part, this is easier actually because we have done the tough analysis. So this thing should be cakewalk for you, this type of analysis. So assumption is IO is continuous. How is IO continuous? Basically this inductor, right, the amount it gets charged, the under discharge, right, discharge is very low, or you can say discharge is very low. So again it comes back to its next current. Okay, and yeah, power electronic device is ideal. So these two are assumptions. So from 0 to T on, what will happen? This switch will be turned off, and as this switch is turned off, right, so I have triggered this switch. As this power electronic device has been triggered, what will happen is this diode will be off. Why? Because if I just measure the voltage, so VD, right, VD will be what? VD will be what? VD will basically minus VO, or it is equals to minus VS, right? So it is negative. So obviously this diode will be off. No matter what, diode will be off. What will be on? Power electronic device will be on, and my output voltage will be Vs. And one more thing is that initially I had assumed that my initial current, just this for the one transient, this for the first cycle itself, and after that things will change. I will explain what things will change. Okay, just for one transient I will explain here, then I will come back to that transient. So if I am starting from 0, right, what will happen is that my IO 0 minus, or IL 0 minus will be equals to IL0 minus will be basically equals to 0 amperes, right? Why? Because inductor would not try to change its current, as some like impulse voltage is directly not getting applied here, right? So that it will keep its previous current. So what will be the voltage across the inductor? So VL0, right, will be basically, so this will be equals to IL0 plus voltage across the inductor. You observe is this total Vs, right, will come across this, because no current is flowing, so all the drop, there will be no drop here, and all the voltage will come across this. So VL0 will be simply Vs. Okay, VL0 will be simply Vs. So which is basically positive, as it is positive, what will happen? As it is positive, my DIL by dt is positive, because V is equals to DIL by dt, and as it is positive, my IL, right, IL will increase, and power will flow from what? Power will flow from source to load. So power will flow like this. For power will flow from source to load. Okay, as this due to this voltage source, like this is energizing the inductor. Okay, and what will be the equation? Basically, what will be the equation of the current? So that is also another interesting fact. What will be the equation of the current? Just keep this down. Equation of current, this is simply what a DC voltage source is connected, and this is simply RL circuit. So it will be simple transient equation. So what is the final value? Final value is Vs by R. It would try to reach to Vs by R. So my IL of T, or you can say Is of T, will be equals to Vs by R 1 minus e raised to power minus T upon tau. And what is tau? Tau is simply L by R. Tau is L by R. Okay, this will be the equation from 0 to T on, right? Then this is just a transient. I'm just explaining the converter in the transition zone. In steady state, right, things will be a bit different. I will explain that as well. And then in the next cycle, when T on, from T on to T, right? Because from T on, what is happening? I am force commutation force commutation, the power electronic device. Okay, so I will forcefully commutate my power electronic device. Next, what is this? So if I forcefully commutate, right, this will be off, and as soon as this turns off, right, inductor wants the current to flow. So the current across the inductor will be some current, let's say IL of T on minus, which is not equal to 0, and the direction of current is something like this, right? So it will want to flow the current. Now here, right, this path is off, this is open circuit, this has only this path, this is the path. So it will obviously turn on the diode, and it will change its polarity. Inductor itself will change its polarity and turn on the diode. So D is on, and as the D is on, inductor will discharge. Basically, inductor will discharge. So my current, chopper current, source current will be 0 in this period, but my diode current will be equals to my output current will be equals to what? It will follow again exponential relation. It has reached to, let's say, IL of T on value. I don't know what is the value, IL of T on, and then it decays, right? E raised to power minus T upon tau. Then it decays, and here, right, it will be T minus T on, because from T on we are starting. Okay, from T on we are starting. Now what next we will do is that it is discharging. Basically, power is not flowing from load to source, but our VL this time, right, VL will be negative. Why it will be negative? You just simply apply KVL, you will see it will be negative. So our VL will be negative, hence our DIL by dt will be negative. DL by dt will be negative, hence our inductor is what? Inductor is actually de-energizing. Okay, inductor is actually de-energizing. Fine. So basically what is happening is that only due to the first cycle, my waveform will look something like this. So the waveform, right, if I just reduce the sizes a bit, waveform will be something like this. It will if I just directly start from the zeroth cycle, first cycle, so it will discharge totally from 0 to some voltage, then it will discharge, charge, discharge, charge. So after this, right, after this the cycle will be like this, right? So here if I again do it in the steady state, now that was a transition zone just for the first few cycles. Then once we reach like 100 cycles after that, right, so basically my inductor will be inductor will have some already current IO minimum, because that is the minimum possible current it can go. Why? Because from 0 I am turning the switch on, before that switch is off, hence inductor was de-energizing through this diode, so it reached to some minimum value. Then as soon as I turn on the switch, again the inductor will energize. As the inductor energizes, what will happen is the current will increase. Okay, that is the reason. So if I talk about steady state, everything will be same, that my VO will be equals to VS. Okay, VO will be equals to VS. My V chopper will be equals to V 0 volts, because it has turned on. My what will be the inductor voltage this time? Inductor voltage will not be directly equals to VS, but it will be something other than that. It will be VS minus VR, right? So whatever the voltage this resistor has, it is that voltage only. So what is the inductor voltage now? It is VL equals to VS minus IO minimum into R. This is the voltage right now. Okay, and of course this will be something positive. We'll assume this will be something positive, because my current will only increase from here. So if my VL is greater than 0, what will happen? My IL will increase, and as my IL increases, what will happen? My IO minimum basically my current increases, right? My current increases, and again what is the direction of the power flow? Direction of the power flow is from source to load. Power will flow from source to load. Okay, so yeah, this is basically the currents, and obviously the diode, this D will be off only. And in the next case, right, in the next case what will happen is that this power electronic device will be turned off. This will be forcefully turned off, and again now inductor has current, the current as IO max, because it was only charging only, so current was only increasing, and just as soon as this is turned off, right, so inductor will de-energize. As this will de-energize, the current will reduce. So current will reduce. As current reduces, my VO will be what? So this time my VO will be 0 volts. Why? Because this diode is turned on, short circuited, right? So this VO will be 0 volts. Chopper voltage will be same only. Chopper voltage won't change. VS, just the currents will change. VS, and my chopper current equals to source current will be 0 this time, right? And what else is there? So here, right, actually my this I didn't write the current expression. So current expression I will write. What is the current expression here? What will be the current expression? So that is IL of T equals to IO of T. What is the current expression? Equals to IS of T equals to, so steady state, what it tries to do, it at steady state obviously it again does the same only, VS by R. It wants to go to VS by R, because this will be short circuited. So I will not explain the transient here. Transient you have studied in network theory. So it will steady state, it will go to VS by R, and it is starting from what? It is starting from IO minimum, right? It is starting from IO minimum. So what can I write? What things can I write? So steady state, this will go plus IO minimum minus VS by R e raised to power minus T upon tau. Okay, so this will be what? This will be VS by R 1 minus e raised to power minus T upon tau plus IO minimum. Basically at T equals to 0, this will get cancelled, only this will be remaining, and at T equals to infinity. Okay, anything I have done wrong over here? Wait, just over. Okay, actually, right. Oh yeah, this equation is correct only because this at steady state it will try to go to 0. Yeah, so here, right, like at steady state the value will be VS by R, but initially at T equals to 0 the value will be IO minimum. Now let's go to here, right. Here basically my source current, chopper current will be 0, but my diode current, which is equals to my output current, which is equals to my ILT. So this will have some equation. What equation it wants to have? So here, right, I will start with IO max. What is IO max? I don't know. At T equals to T on, whatever value I get will be IO max. So I will start from IO max, and I will obviously want to go to 0, right? because like that is my assumption. At t equals to infinity, the circuit, if the circuit is like this only, I'll try to go to infinite 0, right? My current will try to go to 0, so it will be e to the power minus t upon tau. So this will be the equation basically of the second half cycle, like second half, right? This will be the equation. Okay, one thing I made a mistake, but here, right, but from where I'm starting from, that is also we have to take care of, right? So I'm starting from IO minimum, right? I'm starting from IO minimum. So starting from IO minimum, okay, IO minimum. Here one thing I can do is VS by R to go to IO maximum. Yeah, starting from IO minimum, and I want to go towards 0 voltage, right? 0 current. So this will be minus t up, t minus t on, actually t minus t on divided by tau. Because why t minus t on? Because I'm starting from t on here, right? That's why everything is shifted. Everything is shifted now. IO minimum, because I'm starting from IO minimum, not okay. Sorry, not IO minimum. Sorry, IO max. So that was correct only. That was correct only because I'm starting from IO max, not minimum. Sorry. Starting from IO max only, right? Yeah. So at t equals to infinity, what will happen? This will go to 0. But I obviously will not go until t equals to infinity. We'll go until t equals to capital T, right? Then this value will become IO max minimum, because this is discharging. So one more thing in this equation, if you put here t equals to capital T, we will get IO minimum, like our IL of t will be IO minimum. Okay, and at t equals to t on, what will happen? At t equals to t on, this value will be equals to IO maximum. So that's the basic thing basically that you have to understand. And the waveforms will be something like this. So this will be the supply voltage, and the output voltage, it will be 0 because due to the freewheeling diode, as the chopper is off and the diode is on, and it will be totally equals to Vs if the chopper is on. So my output is directly coming across the supply. What about diode voltage? Diode voltage will be just the opposite. It will be on when the chopper is off. So when it is on, so it gives 0 potential, 0 drop, and when it is off, it totally blocks the minus Vs voltage, right? And chopper voltage will be opposite of diode voltage because it is blocking when the diode is on, and it is passing when the diode is off. Same very simple waveforms for this currents. So here next what will happen is about the current waveforms. So current waveforms, you can see I will always ripple from IO minimum to IO maximum. So it will go reach IO maximum, then again it will come down to IO minimum, IO max, IO minimum, IO max, IO minimum. This will be the equations for the currents. Okay, this is the output current, and this output current is also equals to the inductor current for now. Okay, because inductor and the output, like the load, that is R, is connected in series. Okay, connected in series, and drop will be just mimic the current, because drop across the resistor, because it is just proportional to the resistor, proportional to the current. What will be the voltage? So the inductor voltage, right, when this is on, when the inductor voltage is on, it is equals to, let's name this as VL1. Okay, let's name this as VL1, and let's name this as VL2. Okay, VL2. Let's name this as VL1 and VL2. So why am I naming all this? So here, if you observe one thing, let's this time is what, T on. So current is reducing after this. Why is current reducing? Because the inductor voltage is negative. And why is the current increasing? Because the inductor voltage is positive. So, but overall throughout a cycle, right, the change in current is 0. Okay, because it started from IO minimum, ended to IO minimum. And overall cycle, if the change in current is 0, obviously the average voltage will also be 0. That obviously has been proven in the volt second criteria. So if the average voltage is 0, right, what equation I can write? I can write this equation. Okay, from this particular graph, I can write this equation, and this equation we will actually use. This is the equation that we will use for solving most of the cases and deriving formulas as well. Okay, so here the areas are like should be equal, and obviously overall area should be 0 under the time axis throughout a cycle. So here I can write VL1 into T on minus VL2 into T off equals to 0. So VL1, T on is what? T on is alpha into T. So VL1 into alpha, and T off is what? 1 minus alpha into T. So this will be 1 minus alpha into VL2. So VL1 into alpha equals to 1 minus alpha into VL2. So these are the things that you have to understand, and from here we will derive most of the formulas. Next is source, like source current. So source current, right? Source current and the chopper current are same only. Source current is equals to chopper current. This time is for source, it is on when the chopper is on. So for the from 0 to T on, it will be same as the load current, and for T on to 0 T, right, what will happen? It will be off. As it is off, source current will not be like some non-zero value, it will be 0, and this will repeat. Diode current will be just the opposite. So it will be on when the source of chopper is off, and it will be off when the source of chopper is on. And VL voltage, these are same only. So these are the few formulas. Okay, this formula has been already derived to you. I can still derive this formula, okay, for you, that your average output voltage, right, average output voltage will be Vs times T on by T. How do you find it out? Just simply area over the time period. Simple area over time period. That is the formula that I am using. Then IO average. What will be IO average? Simply IO average is basically equals to what? Average is VO average. Sorry, not VO. VO average by R. Why? Because the average voltage across the inductor is 0. So only VO average is left, and I can find out my IO average like this. And IS average will be equals to I chopper average, and it will be lower than the IO average. It will be basically equals to like, as my IO average is I chopper average plus ID average, my ICH average, right, in terms of IO average will be simply alpha times IO average. Why is it alpha times IO average? Because from 0 to T on, this is present. So the area will be what? This area will be simply IO average into alpha into IO average into T on. IO average into T on. That will be the area from 0 to T on. And then I will divide by T, and that will give me the average value of the source current, right? Because my source is present for this whole T time period, but my my load conduction is present for this whole T time period, but for the source conduction, right, source conduction is from 0 to T on only. From 0 to T on only, that's it. That's the only point where my source is conducting. Okay, so that is the case. Next is the RMS, VO RMS. Next is the RMS voltage. So the RMS voltage is this. So this is actually Vs. I will write this as Vs. That will be much easier. Okay. Okay. RMS. How do you find out RMS? Simply, I have derived this, right, previously. In the previous lecture, I have derived this. You just simply square this waveform, rectangle. You square this rectangle, you will get a rectangle itself. Just the this amplitude will be Vs square and not Vs. As it is Vs square, a Vs square will, I can take common, but the time, right? Time will be under root. What is the time? Time is T on upon capital T. So it will be under root alpha, basically. So your VO RMS will be under root alpha, Vs into under root alpha. Okay, your IO RMS will be what? Your IO RMS will be what? 1 by T and this. Okay, 1 by T and this. And like IO RMS, you can compute it like this, or what you can use is, you can use a formula. I will say you what formula, because now I cannot use the formula because the graph is not linear, and it is very difficult to use this formula and like compute all this, right? Very difficult to compute. Okay, this should not be VSVR. Done something. This should be IO maximum. T equals to T on. This is not VSVR. This should be IO maximum. But like, we will not use this, and this will not come. This will not come in the examination. You have to find the RMS value of this weird waveform. This is the weird waveform, right? IO is this weird waveform, and like, it's very difficult to find the RMS value for this. Obviously, I will say you how to do. Okay, this will also be wrong. This will be actually also wrong. This will be IO maximum. This will be IO maximum. Okay, so that is the case. So my output power PO will be PS minus losses. Output power PO will be PS minus losses, right? Like, you use this only to find out the output power. You don't use the other formula. I will tell you what the other formulas are. Now analysis of supply. Until now we have been analyzing the load. What is the analysis of supply? IS average. IS average, again I will use the same formula. This will be from 0 to T on only. So my IS average is actually not present after T on. So if I just integrate up until 0 to T on, what was the expression for the IO, that will work. But I won't do that. I will just do this. IS average I will find out with the help of IO average, because IO average is very easy to find out with respect to VO average by R, right? So your like IO average will be alpha into IO average by alpha into IO average, right? Because it is only present for T on time. Okay, we understand. And IS RMS, again the same, you will square and then take the under root, which is very difficult, and this won't come. Don't worry, this won't come in the examination hall. What will be your PS? PS, right? PS will be simply VS into IS average. VS into IS average. Why? Because this is DC, right? This is DC, so hence I have to multiply DC current. Okay, that's why the PS. And from PS you will be able to compute your PO, because if you subtract the losses, you will get back your PO. So this is the standard relationship between input and output chopper. But you have to remember that your VO average by VS and IS average by IO, this ratios will be equals to alpha. But you have to remember, only valid if IO is continuous. Only valid if IO is continuous, else it is not valid. Only valid if IO is continuous, else it is not valid. Just remember this, keep this in mind, because this is a very, very important point. So now attention, because in the question sometimes if it is not continuous, right, you can't write this, and if you can't write this, you have to go to the derivation. So that's why understanding the derivation is also very important. So from here I can say is that, what I can say is basically, if I cross multiply, right, if I cross multiply, I can observe that my VS into IS average will be equals to VO average into IO average. VO average into IO average. So VS into IS average will be equals to VO average into IO average, right? So this will be my power. Because this is the power, right? This is the power. I surely know this is my supply power. And what is this? So as I assume there is no losses in the converter, so I assume this has my load power. There are no losses. Okay, no losses. Then my PS will be equals to PO. As PS is this, and which is equals to PO, so PO will be equals to VO average into IO average. That's how this comes along. Okay, you have to understand this. Now next, analysis of chopper. Chopper analysis, like the average voltage, right? Chopper, when it is off, it will totally block VS voltage. This will be VS. Total block VS voltage. So as it is VS, all these are VS, right? Yeah, fine, all these are VS. So this will be VS, and this will also be VS. This will be VS only. Like I hope you understood how we did this. Simply find out area under the curve, then VCH RMS, I'm just squaring it, and just time period will get under root. That's why this will be 1 minus alpha into VS. ID average, again ID average, like when is the diode active? Diode is active for T off time. So from T on to T, diode will be active, and if you integrate this, right, you will get this as results. Basically it is the 1 minus alpha into IO average. Then what is ID RMS? ID RMS is basically square and under root, which is very difficult to compute. They won't ask. So these things, right, won't be asked. Okay, and like these things will be asked for a particular condition. What condition is that? That we will analyze in the next few slides. So skip it. Okay, and this one is fine. This one is fine. This one you can skip. Which one? This one you can skip. Okay. This IS RMS values you skip, right? IO RMS also you skip. This won't be asked, but what will be asked, there will be a special case for this particular type of circuit, and from there we'll solve. Okay. So what is chopper efficiency? Chopper efficiency, again I told you the same thing only. It will be PS. This is not PO. PS minus losses. It is PO upon PS. So hence, what is PO? PO is PS minus losses divided by PS, right? That is my PO. That is my chopper efficiency. And like again, if you want to find out the ripple, same formulas. I don't need to explain much. Just one thing you have to take in mind is that you have to make the average inductor voltage 0. So analysis of chopper. One more analysis I will tell here, that the VL average, right? VL average is 0 volts. So this thing is very, very important. From here only we will derive the formulas. Okay, this is a very, very important point. Okay, so now, right, I can comment about the ripple. I can comment about the ripple of the load. I can comment about the ripple of the load. So what is the ripple basically? What is a ripple? So ripple, right? Ripple of load current is what it is. Delta IO equals to IO max minus IO min. That is a ripple, right? If I just take copy and paste the waveform, IO of waveform. So ripple means like how much is the voltage current is changing, right? How much it is changing? What are the boundaries of currents? Not voltage or currents. This time we are talking about currents only. Okay. So here, if I paste this, reduce the size. Okay, so ripple means basically this, right? This from minimum to maximum. What is the difference? How much is it rippling? Okay, how much it is changing? Because I don't want very wide values. I want DC, right? DC means a constant value. So I have to take care of this as well, so that the ripple is minimum. So here, del IO is IO max minus IO min. How do you compute IO max and IO min? I have the expression for from t equals to 0 to t equals to t on. So here what is expression? It tries to go to Vs by R 1 minus e raised to power minus R by L t plus IO minimum e raised to power minus R by L t, right? And IO max will be what? IO max will be the value of this IO of t at t equals to t on. So if I put in this equation t equals to t on, I will get my IO max value. And what will be IO min? So IO min, so this, right? This is after this is closed. Sorry. This not IO min, actually this is I of t. Just hold on. IO of t from t on to capital T on to capital T. Okay, so what will be this? This will be from t on to capital T. And like what will be my IO minimum? IO minimum, if I want to write it in terms of IO maximum, IO minimum will be in this equation. Okay, I have done something wrong here. Okay, I have directly written the expression for IO minimum. Shouldn't have done that. So this, first of all, this is the IO of t expression from t on to t. This is the additive expression. Why? If I put here t equals to t on, what will you see? You will see IO max. And yes, exactly, at t equals to t on, I am getting IO max. And infinity, right? The inductor obviously will go to 0 voltage because freewheeling diode, 0 current, because freewheeling diode is present. It will discharge totally. But obviously in between, the chopper will again get turned on and it will charge the inductor. It will energize the inductor. So it can't go to 0. But the equation will be something like this. So here, if I put, like if I want to find out IO minimum, it is discharging, inductor is discharging at t equals to capital T. It has reached to minimum value. So it will be IO max e raised to power minus R by L capital T minus T on. Okay, it has reached to this value. So this is the value. Now what I can say? I can say is that what is the ripple basically? So if I want to say the ripple, right? Max 1 minus V R. Here it is the IO minimum. Okay, fine. And this IO minimum, right? This IO minimum is this value, and here I have, if I put this IO maximum value here, right? IO maximum is equals to this. If I put this value here, what will I get? So my IO minimum, or what I can do is I can put this maximum value as well. So if I just multiply e raised to power R by L t minus t on both sides, what will happen? I can write IO max as in terms of IO min. So it will be IO min into e raised to power R by L capital T minus T on equals to Vs by R 1 minus e raised to power r by l t on plus I mean e raised to power minus r by l into t on. Right, this is the value basically, this is the equation basically. So if I now bring this IO on the left hand side, if I bring this IO on the left hand side and take common things, so this will be IO minimum into e raised to power r by l t minus t on minus e raised to power minus r by l t on. Okay, and this is equals to what? This is equals to Vs by r 1 minus e raised to power minus r by l t on. I could have written here tau as well. So the best thing that I will do is I will write this tau. Yeah, sorry for the interruption. Actually, I just wanted to put everything in terms of tau because it's just an extra exercise, right? To write r by l every time. So I change everything to tau. Tau is l by r. So here I can directly find out my IO minimum expression in terms of this exponential and Vs by r. What is my IO minimum expression? So if I take this e raised to power minus t on common, right? If I take this e raised to power minus t on common, what will I get? So I just put this in the ratio. So my IO minimum will be Vs by r and 1 minus e raised to power minus t on divided by tau divided by so what I can do is I can take the e raised to power t on common, right? If I take the e raised to power t on common, I will get some value like this. E raised to power t on is common here. This will be should I take e raised to power t on common? What? Yeah, e raised to power t on I should take common. But I can, what else I can do? T minus t on, right? E raised to power minus t on upon tau is there actually. Minus one, right? So now if I just multiply e raised to power t on minus t on here, this will be e raised to power minus t on and this will be minus 1 only. So if I multiply minus on both sides, I will get by my answer as this. So this will be capital T upon tau. So actually my final IO like expression, right? This you can remember actually. This is good to remember. Okay, like you can always derive. I've derived and you can always derive. If your transient is very good, you can always derive. But it's better that you remember this. Okay, that so that you will be able to solve questions very quickly. Minus T1 by tau and 1 minus e raised to power minus capital T upon tau. Okay, so this should be the expression for IO minimum. And similarly, if you want to derive, like if you know IO minimum, right? What is IO maximum? IO maximum is basically 1 this multiplied by IO minimum. Okay, you can simply do it like that. So your IO maximum, just hold on, IO maximum will be equals to IO minimum into e raised to power t minus t on divided by tau. Okay, divided by tau. So we can do it like this. We can find out our IO maximum like this. So if I put this, if I multiply e raised to power t minus t on, right, what will I get? I will get this value only. This will come out to be Like if I keep the e raised to power t at the outside, what will I get here? So t on into this is correct, right? Okay, minus is also there. Sorry. Oh no, minus is not there. This is plus only. This will be plus only. Yeah, this will be plus only. Yeah. So here this will be Vs by R. This will be e raised to power t minus e raised to power t on. This will be minus 2t on. What am I making mistake here? Okay, if I multiply in the bottom, this should remain the same as it is. The top I will remain same as it is. What I'll do, I'll multiply this in the bottom. If I'm, like this will become minus then. So if I multiply this at bottom, just why am I doing this? Just to like keep the format symmetric and all. Else like answer is same only. However you write the expressions. So if I multiply this in the reciprocal, so what I will do, I will add extra minus sign here. So if I add a minus sign, this overall thing will become e raised to power minus t plus t on by tau. Okay, I'm getting cramped out of space. I'll just write the expression, then again I'll come back. Yeah, one mistake I made, like I took this as negative. This should not be negative, right? Minus t on and minus t, this should be positive. So hence our IO minimum will come out to be something like this. Now if I multiply, like I want to find IO maximum, right? If I want to find IO maximum, I'll just multiply. So what equation I will get? If I multiply this t on and t on will get cancelled. This will be IO like e raised to power t, and what else will be present? So this part, right? This part will again be e raised to power minus t. So what will happen here is this will be e raised to power t minus t on divided by tau minus e raised to power t divided by tau. And what will be this? This will be e raised to power. This will be same, right? This will remain as same. This is 1 minus e raised to power t upon tau. This is not 2, mind you. This is tau only. So now what I can do is I can take this e raised to power t upon tau and common. I can multiply this at the bottom. Okay. So what will I get? I will get somewhat like this. Vs by R. This will be e raised to power minus t on upon tau minus 1, then divided by, this will be e raised to power minus t on. So this will be basically e raised to power minus t upon tau minus 1 again. So again I can multiply minus 1 on both sides. Like I'm just want to tidy this one up. This will be 1 minus e raised to power minus t on upon tau, and this will be 1 minus e raised to power minus t upon tau. Now this formula, right? This formula, unfortunately, you actually have to remember. I don't have any option here. You have to remember this. So, like obviously you can derive. It will take you a bit of time, right? So that is a problem. Like you have the backup at least, that if you forget, you can derive it. But it's better to remember this. So I don't ask multiple times to remember many things, but I will ask you this one. You have to remember this, right? This IO maximum and IO minimum. Pretty simple only, because at the top it is always exponential raised to power t on upon tau. But when is the plus sign and negative sign, that you need to remember. The negative sign is in the case of the maximum current, right? Maximum current, and the positive sign is in the case of minimum current. So you can remember it like this. It is the opposite. It is just the opposite. This one and IO minimum. Like if you are also able to remember one, right? Other one you can remember it like this. Okay, so yeah, these two formulas you have to remember. And another thing is input resistance. Again, the input resistance will be same only. It is VSDC upon ISDC, same as like you can derive the formulas. Like VS will be what in terms of VO and IO, and from there VO average upon IO average will be R, and an extra term alpha will be present. Now we'll do the analysis of RLE load. What will be the analysis of RLE load? So again, the same thing, everything will be same, just the equations will be different. In this case, again, the assumptions are same. ID continuous, IL minimum is greater than 0. Okay, it cannot go to 0. It cannot be discontinuous conduction. Power electronic devices are all ideal. Again, for case 1, now I will directly do this in steady state. I have assumed that my initial inductor current is some minimum current IO minimum, right? It is not 0, it is greater than 0. So obviously what is my VO? So here my VO is equals to Vs. My VO is equals to Vs, right? VO is equals to Vs. What is my chopper voltage? Chopper has turned on, it is triggered, so it is 0 voltage. My inductor voltage is what? My inductor voltage, and this time inductor voltage has reduced a bit. What is it? It is basically VO minus IO minimum into R minus E. Okay, so VO is what? VO is Vs. So Vs minus IO minimum into R minus E. So this will be the, like, it will charge, but charge slower, right? It will charge slower, and obviously it is finite. So, and it is greater than 0. That is my assumption. It is greater than 0. Then only this will turn on, right? Else this won't turn on. So obviously the thing is that my IL will increase. And as my IL is increasing, what else can I say? What else can I say? What is the equation of IL? So what is the equation of current, or IO of t equals to IL of t equals to, at steady state where it would try to reach, the inductor voltage would try to go to 0. So at steady state it will be Vs minus E by R, just hold on, plus initial, what is the current? Initial current is IO minimum minus again Vs minus E by R into e raised to power minus t upon tau. So this will be the equation. Basically you can derive the, but you don't need to write this in simpler terms. This is the equation that you need to follow. Okay, this will be the current equation. Okay, and obviously here power is flowing from source to load. Okay, power is flowing from source to load. Now case 2, what will happen? Case 2, right? From T on to T, again this I will forcefully commutate this power electronic device chopper, that is the switch. Then I will then what will happen? Inductor will try to flow the current, current IO max current, because it was charging, so it has increased to IO max. It will try to flow the same current, so it will flow through the diode. It will change its own polarity. So VO this time, VO is 0 volts obviously. And what is my chopper voltage? Chopper voltage previously was 0, now it is Vs, totally blocking this voltage. What about the current? ICH is 0 again. Is is equals to 0. Okay, all these are 0. But what about the inductor voltage this time? So if you observe, right, inductor voltage will be simply, as VO is 0, it is minus IO max into R minus E. So it is overall negative voltage. Is it overall negative voltage? So obviously it is less than 0. So as it is less than 0, what I can say? IL is reducing. So obviously it will reduce to what? Reduce to IO minimum, but actually inductor will behave as if it want to reduce to 0 current. So how will I write the equation? The equation will be pretty simple. My IO of t will be basically IO of maximum initial current e raised to power minus t on upon tau. Minus t on, why? Because the reasoning is simple. T minus T on by tau. Okay, so this is the current. This is the current basically. So it will reduce to this, but obviously it won't go to 0. It will go to IO minimum at t equals to capital T, right? So then the waveforms, every waveform will be same for RLE waveform will be same, except the current slopes and all those things, right? Else everything will be same waveforms, because here just the expression for current is changed, but between what it is rippling, it is rippling between IO maximum and IO minimum. So obviously all the waveforms will be same. Nothing will be different. This formula will also be same. It will be VO average will be equals to Vs into T on by T. It is Vs alpha. V average minus E by R. IS average is ICH average, IO average is same, ID average, all those things same. Just here, right, an extra minus E will come up. Okay, in the IO average, extra minus E will come up. That is just the extra thing. So I will just highlight this. Extra minus E will come up, except that everything will be same as it is, right? Everything will be same as it is. So this all this I don't need to explain much here. I've already explained the previous previous topic. So previous RL load. So everything will be same. Nothing will be different. Okay, so now next what we'll do is we will actually study with the linearized format. Why linearized format? If my tau is very, very less than my capital T, then what will happen, and then how will my things behave, and what will be the ripple voltages. Now let's come to the point where my time constant is very, very higher than the time period. What do I mean by that? So this is the equation, right? So let me just take one example. What is the one example? My IO minimum, not this. Where have I derived it? Ready to go. Ripple is this. Okay, this was for the RLE load, right? So if I find here, what is my IO minimum? If I just I have derived here, right? So this is my IO of T. Okay, this is my IO of T in the case 2. It is reducing from maximum value. So if it is reducing from maximum value, if my tau is very, very higher than T, right? Let's say this is T. Then what will happen? This will be very, very low value. Then I can linearize it. Then what I can do, how do we approximate exponentials? We can write exponentials as the power of x. E raised to the minus x is equals to 1 plus x by 1 factorial plus x square by 2 factorial. But here as this is minus x, so for the odd powers, the coefficient will be negative, minus 1, right? Now, as my x is very, very small, what will happen? I will only keep the linear terms and the terms which are in greater power, right? X square. So if I take the power of 0.1 whole square, it will be 0.01. So it will be very low. So I can ignore that. I can only take the linear part. So my graph, right? Instead of looking like this, it will be almost linear. Why? Because if I compress this, right? If I compress this, what will happen? If I compress this, like this will be almost like a straight line, because this doesn't have enough time to charge and discharge. That's why it gets very low amount of time. And I hope you have studied this in transient. All those things I hope you have already studied. Okay. Or what I can do, if you haven't studied and if you are not able to understand this concept, just study Pulse Response Marathon by Anish Shah. There, if you want to understand this concept, there I have explained this in a detailed manner. Don't have to watch the whole marathon, just watch the initial question, starting question. There I have explained all this, right? So just search that. So if I linearize the things, right? If my tau is very, very greater than capital T, that is time period, switching time period. So what will happen? Everything will be linear. Everything will be a straight line. Okay. Basically, power of x, single power of x. So this will be linear. This will be linear. This is like VL1, VL2. This will be same only, but the current waveforms and all the other waveforms will just be linearized. Why do we do this? First of all, this is anyways happening. This we anyways want. Okay. To reduce the ripples also. The ripples also reduced by a large amount, and for easier computations as well. This is very, very helpful to us. What do we mean by easier computations? Now what will be my IO average? IO average computation has become very simple now, because it is basically what? Output current is basically this rectangle and this triangle, right? Again the same thing. So I can simply write the area of the triangle, which is delta AL into T. So this distance, right? This distance is what? Ripple, that is delta AL. Delta AL is what? IO maximum minus IO minimum, and plus this rectangle. If I simplify everything, it will be IL max plus IL min divided by 2. Now what will be IL RMS or IO RMS? I told you, right? At the starting of the previous lecture, I derived a formula for computing the RMS of these type of waveform, which has rectangle and triangle. So the formula will be IO max whole square plus IO min whole square plus IO max into IO min whole under root, divided by 3 obviously will be there. This will be the IL RMS, that is the inductance average RMS current, or the load RMS current. This is the IO average, that is the load average current, and the inductance average current. Okay. So this is the case. Then IS. What is IS? IS is equals to ICS, that is chopper current. It is in series with the chopper. So it is equals to IO of T for alpha between 0 to T, because when the chopper is on, it is same as the load current. When the chopper is off, it is equals to 0. So how can I compute the average? Again, right? It will just contain the area from 0 to T on of the current output. So basically, it will be alpha times that, right? Alpha times IL max plus IL min divided by 2. You can compute with the help of graph as well. This is my IS, right? This is my IS. So if you want to compute this rectangle and this triangle, your result will come out to be this. I don't have time to derive all this, but this is simple basic mathematics. So I hope you can do this. Again, what will be the RMS? Just the under root of this alpha, right? Just the under root of the alpha. Again, the same reasons, as everything is linear. If I square, then take the under root. The common terms will be outside, and the time will get under rooted, right? It will be under root. So that's why this is under root alpha, and this expression is what? This is IO average, and this expression is IO RMS, right? Already computed all those things. And what will be ID? ID is equals to IO when my chopper is off. So the second case. So again, this will be 1 minus alpha, because this is the case for the duration of T off, not a T on. So this average will be 1 minus alpha, and again, if I want to compute the RMS, it will be 1 minus alpha whole under root, same reasons, into IO RMS. So these are the equations basically. Now one thing what we can do is, we can analyze the inductor current for linear case. So for linear case, if I want to analyze the inductor current, then I can do the computation for ripples. So there the computation was very difficult. If you remember the formula, right? IL max and IL min, the computation was very difficult. Here the expression will come out to be very, very simple. What is the expression? So when the chopper is on, right? When the chopper is on, what is my voltage across the inductor? The voltage across the inductor is Vs minus Vr minus E. That is the voltage, right? And when the chopper is off, the voltage across the inductor is minus minus Vr minus E, right? Now one thing I know is that what is the voltage across the inductor related to current? It is basically L times change in current. So I can write L times delta IO by T on. How can I do this? Because the period of time is very small. So I can, instead of writing D, I can write it delta IO. I can write, as the time period is very small. What is delta IO? Delta IO is a change. So what is a change basically? Change is basically from minimum it is going to maximum. So what I do? I write final minus initial, right? I write change. Change means final minus initial. So initially it was IO minimum. Finally it is IO maximum. So this is a change in current divided by change in time. So what is the change in current? IO max minus IO min. What is IO max minus IO min? It is delta IO. And what is change in time? It is 0 to T on. So T on minus 0. So it is delta T, right? So delta IO divided by T on equals to Vs minus Vr minus E. Okay, so next what will happen? Minus L delta IL divided by T off equals to minus Vr plus E. Okay, yeah, this will be L delta IL. So this is for the on period, the expression. This is for the off period. So from both cases, right, you will be able to find out the change, like the ripple in the current. So I will just make this IO, because IO and IL are same only, but same things are there. So here, right, actually it is minus delta IO. Why is it minus delta IO? The reason being is that basically here the current is reducing. Actually I am going from maximum to minimum. So finally is minimum, initially is maximum, so it becomes minus delta IO L into, and the duration is T off during the off period, and obviously here the voltage is negative, so it anyways gets cancelled. And if you want to do the derivations, right, if you want to do the derivations, basically for case A, your okay, what have I done? For case A, right, I want to find out the, I want to write my Vs in terms of this delta IL and stuff that I want to find out. Okay, so for case A, I want to write my delta IO, right, no, in terms of Vs and E, not in terms of not in terms of this VR, because VR is unknown to me. I know E, I know Vs, but I don't know VR. So I want to write my delta IO in terms of VR. So exactly that is exactly what it will do. And I am assuming the current is almost, the ripple is very low, current is almost constant. So the drop in the resistor in this case and drop in the resistor in this case are almost same. So VR in the case 1 is this value, VR in the case 2 is this value. Now if I equate this, right, equate the VRs on the both sides, I will get Vs, minus E will get cancelled. So Vs will be left out here, and I will take this on the right hand side. So Vs will be L delta IO into 1 plus T on plus 1 by T off. So you can remember this, or you can derive. That's up to you, right? How much time you take to derive. I will also share a few shortcuts. How can you remember this? Okay, without doing all these things, right? I will also say a shortcut. But for now, you can remember this, or I will share the shortcut to you how to remember. Now if you put the expression of T on and T off in terms of the switching period or in terms of the switching frequency, then what will you get? You will get, this will be Vs, I can put this L here, I can put this T on and all those things. After reframing the equation, you will get Vs alpha 1 minus alpha into T by L, or T I can write as switching frequency as well. So this will become 1 by Fl, Vs alpha 1 minus alpha Fl. Okay, so here what will this be? Here what will this be? This will be right. This will be right. This will be basically very important formula. Okay, so this also you can remember, or I will tell you a shortcut how to remember. That also I will tell. Don't worry. Now Important points to note about the ripple of the output current. Ripples of output current is independent of RLE. So it does not ripple, right? Overall ripple. Ripple means the maximum minus minimum. How much, is it varying from the average? That is the main purpose, right? We have to be as close to the average as possible. So ripple actually is not a function of RLE. It is independent. Ripples of output current only depend on the inductance. So if my inductance is very high, the ripple will be very low. You can see, right? If my inductance is very high, the ripple will be very low. If my switching frequency is very high, the ripple will be very low. Okay. So actually, right, it does not depend on the load, right? It does not depend on the load parameters. It is independent of load parameters. Okay. So with the help of the device itself, I can understand, like I can keep the ripple as minimum as possible, right? So actually, yeah, that is the case. L is here, alpha L, and like ripple is function of alpha L, F, and Vs. All these are either supply parameters or either the chopper parameters. Now what is my IO max? Basically, right, IO max is what? This maximum value, right? What is happening? If my IO average will be somewhere around here, in between, exactly between the ripple, right? IO max will be somewhere around here. Okay. IO average will be this, like IO average will be between IO max and IO min, and here, right, this will be the half the ripple and this will be the half the ripple, like the distance from the average to the maximum will be half the ripple, and the distance from the average to the minimum will be again half the ripple. It will be exactly at the midpoint. You can compute all these things, already explained, right, here, like here as well. Whenever we have tried to compute this IO average, what did it go here, right? It was IL max plus IL min divided by 2. So if I want to write this in terms of delta, you can write, right? So like you can change this in terms of delta, and then you can follow. So what is your delta IO? Delta IO is basically IL max minus IL min. So you put delta IO plus IL min equals to IL max. So you replace here delta IL plus IL min. So what will happen? This will be 2 IL min and delta IO. I will divide. So this IO average will be equals to IL min plus delta IO by 2. Same thing, right? Same thing. So you can do that. So that's how we get, like it is at the midpoint. So IL max will be this, IO max will be this, IO min will be this. Like IL and IO are interchangeable. If I ever speak IL and IO in step down chopper, they are the same thing, because inductor current and the load current are the same. They are in series. Okay, just don't get confused by that. Now, few important points you need to find out is the about the duty cycle and the critical value of inductance. So here we want to find out the boundary condition for which actually the device actually is just on the boundary of conduction. So first of all, I will find the critical value of duty cycle. So the value of the duty cycle for which the device is just conducting. It will stop conducting after that. It is just conducting. So my IL minimum, right? IL minimum or IO minimum will be 0. It is at the boundary of continuity and discontinuity. Just I think in the previous rectifiers also we know what this boundary means. So as this is a boundary, right? That's why this is the name speaks for itself, that it is a critical value of duty cycle. So my IO max will be delta IO. IO average will be delta IO divided by 2. Okay, because my IL minimum has gone to 0 and my IL minimum value was this only. IL minimum value was this only. So it is equals to IO average minus delta IO by 2. So this has 0. So IO average will be delta IO by 2. Okay, delta IO by 2. Exactly that. So why is it so interesting to us? It is interesting to us because this was the equation, right? This was the delta IO equation. This was the ripple equation, and this is just continuous. So this equation is still valid. So I will replace my delta IO with what? I will replace my delta IO with IO average. 2 IO average. Delta IO will be 2 IO average equals to, what is this? Vs into alpha is changed to alpha critical, because this is the critical value of alpha for which I am just continuous. Alpha C into T, or I can write F as well, doesn't matter. F into L. Okay. Okay. So IO average will be what? IO average is what actually IO average, if you remember, right? If I don't have E, right? So assume this is only assume for RL load. For RL load, what can I say? RL load, I can directly say that my IO average will be VO average by R. And for a step down chopper, if you remember, I derived the VO average formula. It was alpha into Vs by R. Exactly, that is what I will replace. So for RL load, I will replace this. Okay, so basically, have I done it already here? No, this was the analysis of inductor current. So here, if I replace everything, right? Just do this. Just hold on a second. I'll just replace everything. This value will be simply 2 times alpha into Vs by R equals to Vs. This is alpha C, right? Alpha C. Alpha C Vs alpha C into 1 minus alpha C divided by FL. Right. So what will happen? Alpha C will get cancelled. Vs will get cancelled. I just want this expression. So this will be 2f times L equals to, now there is R here, and this will be 1 minus alpha C. So alpha C will be 1 minus 2FL by R. So this will be alpha C. Do you need to remember this? No. Just remember that formula, right? Just remember that formula. What formula? This one. Okay, you can remember this one, or this one also you can derive. And from here you can come to here, right? How you can come? Just how I came. Okay, no need to remember. You can derive. So my recommendation will be derive. If you want to remember, obviously you can always remember. That's up to you totally. So my recommendation will be derive. Now next is same analysis of inductor current for the critical value. This time, right? Critical value of inductance. So I'm just, what is happening here, right? I was reducing my alpha. So as I was reducing my alpha at max can be what? Alpha at max can be 1. Okay, if my R is infinity, alpha at max can be 1. But alpha minimum will be 0 only, and here we can see that duty cycle ratio is actually depending on the this resistor and frequency, all those things, right? And inductance. So what is the critical value of inductance? Again, same thing I will do. That for critical value of inductance, I'll just replace L with LC. And if I do the same thing, just as I did for alpha C, if I do the same thing, I will get my expression of critical value of inductance like this: 1 minus R in 1 minus alpha into R divided by 2F. Just do the same derivation and same thing. So this also I will recommend you to derive. Just remember, like if you can remember this. If you like, I will tell you a shortcut how to derive this as well. Don't worry. Okay, so you can derive this as well from this. So this is the mother formula, and from here you can derive all the other formulas. Okay, critical value of alpha. So another thing there can be, right, critical value of switching frequency. So here, right, instead of this, if I replace my FC, if I replace this with FC, so basically critical value of switching frequency, like you can remember this as well. Like this is the critical formula. So if I replace L with L will be a just simple value constant, but if I replace F with FC, everything will just be flipped. So it will be 1 minus alpha divided by 2 LC divided by 2L, because L is constant value. Okay, okay. So FC is equals to 1 minus alpha into R divided by 2L. So let us basically summarize everything, whatever we have learned. Let us quickly summarize that these are the formulae, and which ones you need to remember. You can remember this. Okay, you can remember this formula, and yeah, that's pretty much it, right? All this you can derive, right? All this you can derive. You can remember this formula, and with the help of this formula, you can derive this. So this is the recommended, and remember this is for the RL load only. These formulas are valid for RL load. So this is the recommended one that you should remember. Okay, only this formula, right? Others you can derive. This is for a step down chopper, and remember what is the condition? Condition is IO is continuous, load current is continuous, and switching frequency is very, very high than the critical frequency, right? At this frequency, like it will be just continuous. And it will not be it will be linear though. Actually, my switching frequency, right, must be very, very higher than the very, very higher than the R by L, right? R by L basically very, very high. Then I can linearize. Why? Watch that video, pulse response marathon video, just the starting question, and that should be enough. And another few criteria which we have used here, like what you need to remember. You need to remember all these conclusions. Remember? No, you can derive, right? Just understand how did I derive all this. That's the important point. And this formula you can remember, or how did I derive, that also you can remember. Then two things we will use in like volt second criteria and amp second criteria. In this lecture we have used volt second criteria, and in the next lecture with the help of capacitive filter we will use amp second criteria. But before that we'll do few more questions, and the next lecture we'll do few more questions, and we'll wrap up our step down chopper with capacitive filter, and that will wrap up step down chopper, and after that we'll study about step up chopper. Thank you for watching, and I will see you in the next video.